This is MACFIS, the Modular Automatic Camera Focusing System. Our team was tasked to create an automatic system that could twist a lens into its respective camera for two different cameras placed in aircraft worked on by our sponsor, Parker Meggitt. The current technique used by Parker Meggitt is to have a technician twist the lens manually based on an optical diffraction chart and estimate where the camera is focused based on the patterns created by the camera looking at the chart. This is an old technique used to tune TVs in the 20th century. The team decided a more modern approach by using a laser, beam expander array, and a stepper motor to twist the lens automatically based on the GUI input of the technician.
There are two main standards used for our project. The first is MIL Standard 5.8.6.3.1, which is the standard specification for ergonomically sound weight. This standard was used to ensure that the final system was considered transportable according to military standards. We applied it when purchasing or printing parts to ensure that the total weight of our system did not exceed 37 pounds. The second standard our project primarily used is the standard specification for the laser level. This standard was used as part of the system's safety requirements. Our final system's laser is below Class 3A, so it is considered eye-safe according to this standard. Our initial design was based on several trade studies regarding the mechanical design, optical design, the gear-lens interface, the belt-gear interface, and the lens movement. The criteria used for each trade study involved schedule, performance, and cost. After performing the trade studies shown, our initial design was a single laser for focusing, a gear and smooth belt for rotating the lens, magnets for fastening the gear to the mechanical base, and a kinematic mount for moving the lens.
Shown here is the optical layout for the modular focusing system. The first two lens elements are a positive and a negative lens forming a Galilean beam expander. This expands our 3mm laser beam into a 15mm beam. For the CMX cameras, this collimated beam is projected directly into the camera lens to focus the camera at infinity. When focusing a CDSS camera, the third aspheric lens is included, bringing the laser light to a point about 1 inch in front of the camera. When the camera has a sharp image of the point, it is appropriately focused to objects very close to the camera. The lenses chosen for this task were carefully analyzed to ensure nearly diffraction-limited performance. Shown here is the SOLIDWORKS model of our optomechanical assembly, where we have imported the ZMAX lens layout with the ray diagram into SOLIDWORKS to demonstrate the layout. If we take a cross-section of the system here, we can see the laser projecting through our 3 neutral density filters, which attenuate the laser power so that the camera isn't oversaturated. We have our negative lens, followed by our positive lens to perform the beam expander. We have our shear plate interferometer, which verifies collimation of the laser light, which is a critical part of this process. The aspheric lens pops on and off here and produces a virtual object in front of the camera lens. And we can see where the ray diagram shows that the image is formed right at the camera sensor.
The modularity of this design is dependent on the optics, where we have used an aspheric lens with kinematic mounting capabilities to change the focus location of the laser source for each camera. The aspheric lens changes the beam focus from being focused far away for the CMX camera and changes it to focus significantly closer for the CDSS. This lens exchange, along with 2 kinematic camera plate mounts for both cameras, allow for an easy switch between these cameras while maintaining high repeatability for lens focusing.
For the mechanical side of the project, we needed a quick and simple way for the technician to install each camera stand, with the system still working reliably. Early on in the project, we determined that a gear and belt system would be the best approach, where a gear attached to a servo motor would rotate the lens using a belt connected between them. The mechanical assembly has 3 major parts: the servo motor, the tensioner, and the camera stand. The camera lens has a removable gear around it that only needs to be attached when the system is operating. The tensioner sits between the servo and the camera stand. We designed the tensioner by making a small stand that has a ball bearing that can slide vertically up or down to increase or decrease tension in the belt. To swap out cameras, the technician could slide the bearing down, thereby loosening the tensioner, allowing them to remove the belt from the lens and pull out the camera stand. Early on, we first designed using a smooth belt and smooth gear, where the gear only had a small groove for the belt. This was effective for some tests, but depending on the lens we used, the smooth belt did not provide enough tension to rotate the lens. So we redesigned to use a toothed belt and gear, which proved much more reliable. This new design also allowed us to use more off-the-shelf parts, decreasing the amount of custom parts that are needed, making it easier for our sponsor to replicate the system if they need. The entire mechanical assembly sits on a large mount that can easily be attached to the breadboard. This mount is tall enough to allow the camera lens to be properly aligned with the laser. Lastly, we designed a stand to hold the power supply. The cables running into and out of the power supply are fragile, so we wanted to permanently mount the power supply to the system. With a power supply mounted in this way, there's less risk of the technician damaging it by accident.
The main program of our system is a Python script using the IDE Notepad++. This is where the spot size is determined, which is accomplished by using the image processing library OpenCV. Using the library, the program reads in values of the pixel intensity and uses that data to determine the size of the beam. This script communicates serially with the Arduino, which is used to rotate the motor based on spot size. The Nano will issue commands to the motor in proportion to the spot size, meaning the greater the spot size, the greater the rotation. The team has decided to change from using a Raspberry Pi to an Arduino Nano and from using C++ to Python due to preference. When the software is run, a display of the camera as well as the spot size is shown, which will get smaller as the motor rotates. When the spot size is at a minimum, the motor will stop rotation and the program will close. The camera is now in focus and the lens can be tightened. The GUI is used to select the camera and to start the focusing process, and may also be used as an emergency stop.
To start, the technician will place the can into the designated stand. Next, the technician will put the lens into the lens adapter and attach a magnetic gear coupler. After, they will attach the adapter to the servo stand and tension the belt around the gear coupler. Next, they will plug the can into the lens sensor board, the system to the power, and the system to the computer. Finally, the technician will select the camera type on the GUI. Once the focusing is complete, the technician will then lock the lens into place and remove it from the system.
Our results in verifying the accuracy of the camera focusing system are equally dependent on the working components of the optical assembly, mechanical assembly, and electrical and software integration. The software can detect the focused laser beam spot at the predicted spot size equivalent to the accepted 4 to 6 pixel width value. This margin gives us an accepted focus of about 90 to 95%. Based on our focusing metrics, when comparing to the Parker Meggitt acceptance test procedure, their camera focusing technicians verified that our automatic focusing method passed for the both CMX camera, the camera located outside the aircraft, and the CDSS camera located inside the cabin of the aircraft. One important factor of the automatic camera focusing system is the time it actually takes to focus one of these cameras. After the camera is in place in the kinematic camera stand, the software is initiated and takes less than a minute to complete the rotation of the lens to an acceptable focus. The time taken to focus each camera will ultimately allow for high repeatability for camera focusing, as well as increased production speed for each camera.
For final verification, we went to Parker Meggitt, used our system to focus both lenses, and had a technician for each lens use their method to check if our method was considered to their standard. The technicians were able to verify that we had accurately focused the lenses, and our system was a success.